Let me just start by saying that it's a real honor and privilege to be speaking at this conference. And it's been a very well-organized, streamlined conference, and I've been very impressed by all the organizers. And I've also been very impressed by all the talks today. It's always great to see what young people are working on and what the new and upcoming projects are in the field. And there was a very broad range of very rich talks today, and I learned something from all of them. so thanks very much for that. It's too bad we can't meet in person. There are so many benefits to actually being in the same place at the same time and being able to carry on the discussions afterwards and so on. I mean, I know there's also pros to doing it remotely, because some people who might otherwise not be able to participate are able to participate. And also we decrease our carbon footprint, which is always an important consideration. So I don't know what the world is going to look like in the coming months and years, but I guess we'll have to strike a balance between the need to meet in person, at least on occasion, and also to capture some of the benefits of this kind of remote technology. So anyway, I hope that we can all meet in person sometime soon. I wanted to, just before I start, just mention that I changed my title just today to make it clearer how this talk ties up more plainly with one of the themes of this conference. The talk is entitled "Why the Past Matters: Scientific Taxonomy and Historical Explanation." And I'm going to try and show the link between taxonomy and explanation in the latter half of the talk. So, I won't be talking about explanation until somewhere towards the end, but I think it should be clear why I think taxonomy and explanation are related. So I'm going to start by talking about certain skeptical doubts that people have had about the importance of historical taxonomy or taxonomy based on historical properties. And then I'm going to explain a little bit more what I mean by a historical taxonomy or historical classification, a classification, in other words, that sorts phenomena into historical kinds, or as I'll prefer to say, etiological kinds, and I'll explain why I think etiological kinds is a better term than historical kinds, although some people use them interchangeably. I'll also talk a little bit about some of the precedents in the philosophy of science for discussing etiological kinds, going back to the 19th century. And then I'll survey a very broad range of examples from a range of sciences of etiological classification schemes or etiological kinds. And these derive from cosmology, astronomy, geology, biology, and linguistics. And I'm doing this partly to give a sense of the range and diversity among etiological classification schemes and to bring out some of their common features. Then I'm going to move on to talk about why, how to justify classification by etiology. And I'll do so by linking it in part to a scientific explanation, and in particular, historical explanation. And then I'll try and draw some general conclusions. I'll also pose a bit of a puzzle at the end, and I would invite people, welcome people's attempts to help me out solve the puzzle or resolve what I take to be a bit of a problem that I think I have a partial solution to, but I'm not entirely satisfied with. So that's the plan. So the general question here is, does history matter to science? Does a study of the past matter to scientific inquiry? Now, this is not a question about the history of science, because there's a debate, of course, about the importance of studying the history of science to understanding science, to understanding scientific method, to understanding scientific inquiry in general. And philosophers and historians of science and scientists themselves have contributed to that debate. But that's not the debate that I want to try and engage with today. The debate that I am more interested in addressing has to do with the question of the importance of studying the history of the phenomena that are studied by the sciences. Does it matter to science what the history of the phenomena that are under investigation, what that history is? In particular, should we classify and explain such phenomena with reference to their history, or does history not matter? Is history irrelevant? And if it does matter, when does it matter and how does it matter exactly? Now, I think some philosophers of science have given a voice to the idea that history shouldn't matter. And the reason that they give is that the only thing that matters to scientific inquiry, to scientific explanation, to taxonomy, is synchronic causal powers. So you study phenomena, you investigate their current causal powers, and that's all that's important to understanding how they're going to behave in the future, in predicting and explaining and so on. So the idea is that two tokens of a type that differ in terms of their historical properties don't differ from a scientific point of view. And classification into natural kinds should always be based on current causal properties, not on the histories of the phenomena under investigation. So you can find this view among some philosophers, mainly metaphysicians, but also I think philosophers of science. So Brian Ellis, who is approaching it from an essentialist standpoint, but I think this view is also espoused by non-essentialist philosophers. I think Jerry Fodor has said things of this kind in various places. But Ellis says the essential properties distinctive of any natural kind must be independent of the histories, locations, and surroundings of its members. And you might think that one way of sort of bolstering or making this claim a little more plausible is to think about something like, say, two molecules of a certain substance. Take two molecules of ammonia, NH3. If one of these molecules is secreted naturally in the human body by kidneys to neutralize acid, and another is mass produced in some industrial process, which is standardly used to produce ammonia in various industrial contexts. If two such molecules are intrinsically indistinguishable, why should we ever classify them differently? What would be the impetus for distinguishing among these molecules based on their history or based on the way they were produced? What matters to a scientist is their synchronic causal powers or causal properties. Now, to try and respond to this challenge, I'm going to look at various examples of etiological or historical classification schemes in the sciences. But before doing so, I want to try and characterize what I mean by historical or etiological classification. So etiological classification, as I understand it, is based on shared causal origins or histories or trajectories. So etiological taxonomies categorize phenomena into etiological kinds. The results of these kinds of classifications are to identify various etiological kinds in the world, in the universe. And I think we can distinguish two subtypes, and this distinction is thanks to the philosopher of biology, Laura Franklin Hall. And she says, she uses historical kinds, but I'm transposing what she says a little bit into my terminology. She says token etiological kinds are ones that share a token causal origin or a history or trajectory, whereas type etiological kinds are ones that share the same type of causal origin. So in the first case, they can be traced back to the very same origin or history. In the second case, these origins or histories are of the same type in some sense. Another distinction that can be made here is between pure etiological classifications and hybrid ones. So some etiological kinds are hybrid rather than pure. What do I mean by that? Well, members of pure etiological kinds do not share any synchronic properties that are not also shared with members of other kinds. So the only things that they have in common is their causal history or their causal origin. But so an example of that would be, and I'll go back to this example in a few minutes, igneous rocks in geology. They have diverse compositions. They have nothing in common except there being rocks, which they share with non-igneous rocks. But all igneous rocks do not share any intrinsic properties. What distinguishes them is that they are they're formed by the same process. By contrast, members of hybrid etiological kinds share some synchronic causal properties not shared with members of other kinds. So typically biological species, for instance, share many properties not shared with members of other species. There are some exceptions to this. There are some species where you have, say, extreme sexual dimorphism, where they have very little in common. Members of these species that distinguishes them synchronically, and more or less the only thing that distinguishes them is their causal history. And by the way, I'm talking about etiology because I think what's crucial here is not just history, pure and simple, but causal history or causal origin or causal trajectory. Now, this idea of etiological classification or etiological kinds is not entirely new. William Whewell in the 19th century talked about what he called it paleo-etiological sciences. And he calls it paleo-etiological. The paleo here refers to ancient or to history, and the etiological refers to causality. I find paleo-etiological to be a bit of a mouthful, which is why I shorten it to etiological. And I know that sometimes people use etiological as a synonym for causal, but I'm using etiological to mean causal history, which is the way it's used, at least in some contexts, in science. So Whewell was interested in these sciences that classify on the basis of causal history. And he says the following in his Logic of the Inductive Sciences: the class of sciences which I designate as paleo-etiological are those in which the object is to ascend from the present state of things to a more ancient condition from which the present is derived by intelligible causes. And Whewell included among the paleo-etiological sciences geology, philology, archaeology, and also parts of astronomy. And classification, he thought, in these sciences is at least sometimes based on shared history. So in philology, which is the study of languages, today we might say linguistics, language families are a kind of classification based on history, shared history. But I would say other sciences also regularly classify on the basis of causal history, including cosmology, evolutionary biology, paleontology, of course, and also linguistics, as we would say today. Now, I don't think it's useful to think of the historical sciences as being a separate class of sciences, because I think most, or if not all, of these sciences contain some historical classification schemes, but they also sometimes use taxonomies that are not historically based. So I don't think we can delimit a class of sort of exclusively historical sciences. And I think this is true of really all the sciences mentioned here, that they at least partly classify on the basis of history or causal history. More recently, Ruth Millikan, philosopher of biology, philosopher of cognitive science, introduced the term historical kind. And she, though, identifies it, I think, with a subclass of what I'm calling etiological kinds. She also calls these copied kinds. And these, I would say, are both token etiological and hybrid. Token etiological in the sense that for Millikan, they have to share the exact same origin or history, the same token history or origin. And they're also hybrid because they tend to share synchronic properties in common. And the reason I say this is that she associates three features with what she calls historical kinds or copied kinds. One is reproduction. They're all members of these kinds have been produced from one another or from the same models. And I think mainly she has in mind biological examples here, though she also mentions artifacts and how artifacts are produced from the same blueprint. So if you have a certain car model, then all cars of that kind come from the same specific token origin, and they've been reproduced as a result of having the same template or blueprint. They also are produced by or in response to the same ongoing historical environment, including other copied kinds. And this applies mainly to biological copied kinds, I think. And then finally, they all have some function where she has a particular understanding of function. But these features, I think, don't capture the full range of etiological kinds that we find in the sciences. They capture at best a subset, which I would prefer to call copied kinds following her. She sometimes calls them historical kinds, but I think that is just a subset of what could be considered etiological or historical kinds. So this, I think, is a special case, not all cases. So here, these are some precedents among philosophers of science to identify etiological classification and the sorting of scientific phenomena into etiological kinds. And now I want to move on and look at some examples to give a sense of the range and diversity of etiological kinds in the sciences. So in cosmology, there's a category of cosmic microwave background radiation, which is electromagnetic radiation from the early universe. It's a relic of the Big Bang. And cosmologists identify this type of radiation not on the basis of its synchronic properties, that this radiation has a distinctive frequency, it also has a distinctive temperature, but the reason that we classify radiation of that type as CMB radiation is because it originates from the very first moments after the Big Bang. So even though all instances of cosmic microwave background share their synchronic properties, that's not the basis for identifying them. And to sort of drum that point home, you can think of producing radiation in the lab with the same temperature and the same frequency. Of course, that wouldn't be CMB radiation because it doesn't have the right origin. So instances of CMB, I would say, constitute a pure, not a hybrid etiological kind, because they don't share any properties that are not also shared with non-instances, say something produced, a burst of radiation produced in the lab artificially that doesn't originate from the Big Bang. So you might say, why do we classify them in a taxonomic category? Why do I identify them as a distinct kind in cosmology? Well, I think the answer is primarily because CMB radiation provides very important information about the early universe, about the Big Bang and what happened soon after the Big Bang. By studying the properties of this kind of radiation, we can infer many things about the very early history of the universe. What about astronomy? Well, a nice example from astronomy would be the class of meteorites. So meteorites are just rocks that originate elsewhere in the solar system. They're found on the surface of the Earth. You can sometimes talk about lunar meteorites, but we usually are concerned with terrestrial meteorites. And they don't share many intrinsic properties. One intrinsic property that a lot of, or almost all meteorites possess is a fusion crust on their surface, and that's a result of them melting due to heat on exposure to the Earth's atmosphere as they travel to the Earth's atmosphere. So many of them develop this kind of thin layer on their surface, which often is used to identify them as meteorites, but that's not what makes them meteorites. We classify them together because of their origin, because of their history, because of their causal trajectory, and that's due to the fact that they provide clues to the timing and formation of the planets and other vital information about the solar system. So they don't always have the same token origin or even the same type of origin, but they are identified based on the same type of causal trajectory. So I think here there's room for distinguishing causal origin from causal history and causal trajectory. And with meteorites in particular, it's not so much the origin or the history, it's the causal trajectory that distinguishes them. And it's the same type because, they travel through the solar system and enter into the Earth's atmosphere, but they don't do so all at once or at the same time. They've done so for many eons in the past and will continue to do so, I guess, in the future. Geology is also a rich source of examples of etiological classification schemes. So the primary classification scheme in geology is the classification of rocks into igneous, sedimentary, and metamorphic. And this is, of course, based on etiology because igneous rocks are a result of a process of solidification and crystallization of lava or magma, whereas sedimentary rocks are formed when small particles are transported and then later compacted to form larger rocks. And they can have both sedimentary and igneous rocks are very heterogeneous in terms of their composition, in terms of their intrinsic properties. What distinguishes them is the process by which they're formed. So they can contain a variety of minerals, of materials, but really what is distinctive about them is the process by which they come to be formed. And so I would say that these are pure etiological kinds. They don't share any synchronic properties that are not shared with other kinds. And they're also type etiological, not token, because they can be formed at various different times during the Earth's history, or indeed even on other planets. So the thing that distinguishes them is the same type of process that leads to their being formed in each case. Biology, of course, I think is maybe a better known example. Species, I've already mentioned, can be considered an etiological classification scheme. Now, these are token etiological kinds because members of species all share common ancestors. So they all originate in the same group of organisms in the past. And typically biologists don't consider something to be a member of a species unless it has the right origin. As I said before, they also typically share a lot of synchronic properties. So you can think of them as being hybrid because they are not individuated solely on the basis of their origin. Homologies are another interesting case of a etiological kind in biology. In this case, we identify phenotypic features on the basis of their diachronic properties. And this is to be contrasted with a classification scheme which looks more at synchronic properties. So biologists and philosophers of biology talk about the distinction between homologies and analogies, where analogies are distinguished on the basis of their synchronic properties or their causal functional profile. So if you think of, say, wings in birds and bats and in insects, they have different origins. They're classified as wings because they have certain kinds of similarities when it comes to their functional properties and their adaptive features, whereas homologies might be very different functionally, but we classify them together based on their origin. And I should say, in many of these cases, these classification schemes can coexist very nicely within the same broad science. So you can have an etiological classification scheme and a non-etiological or synchronic one that coexist quite nicely alongside one another and need not compete with one another. Now, again, here, the reason for identifying homologies, I think, is primarily because it provides information about causal history, about the process of natural selection, the kinds of selection pressures that organisms were subject to, and how those selection pressures changed and shaped various phenotypic features within different lineages in the biological world. My final example is from linguistics. And here again, sometimes linguistics classifies on the basis of synchronic features. So linguists sometimes talk about typological categories in different languages, and these are not etiological classifications. These are classifications on the basis of functional properties. So sometimes we identify verbs in different languages, in unrelated languages, based on how they function within the language, what role they play with respect to other parts of speech, and so on. And this is what's called in linguistics a typology. And this is a way of identifying these features across languages in unrelated languages. But also linguists like to identify what they call cognate categories. And these, I think, are etiological in character. So this is a classification that is based on the origin or the history of these linguistic features, whether they're words, morphemes, syntactic structures in some cases, and so on. So this is an example of a syntactic structure that is a cognate structure. So here's a quote from a linguist. Modern German subjunctive mood has almost no functional overlap with the English subjunctive, but both are known by this name because they derive from the same Proto-Germanic form. So they have the same history, they have the same, the same origin, and that's why we classify them both as subjunctives. This linguist goes on to say the term subjunctive is not used as a comparative concept here, but as a label for a cognate set. And by a comparative concept, I think he means roughly what I just meant by typological category. So it's not that they play the same role within the language, rather they're identified as subjunctive constructions because they share the same origin. And one reason for classifying them together is to understand the process of language change, how these structures which share an origin evolved and were modified in the process of linguistic change. In different contexts. I'm not sure if people can still hear me. I just got a message saying that my my microphone wasn't on, but unless I hear otherwise.
You cut out for a minute, but you're good now. We can hear you. Yeah.
Oh, good. All right. Thanks, Zelda. So now that I've surveyed a very wide range of examples, I've bombarded you with a wide range of examples of what I'm calling etiological classifications. I want to try and consider the question, why we classify on the basis of etiology. And I think these examples bring out two main reasons, as far as I can tell, for classifying on the basis of etiology or causal history. And one has to do with retrodiction, or prediction of past events or past goings on. So sometimes we classify on the basis of etiology to provide information about the origin or the causal trajectory of a certain phenomenon. And this seems to be the case for cosmic microwave background radiation, or, as I said, it tells us a lot about the Big Bang. Or for meteorites, we can then trace back their trajectories and figure out something about the formation of planets in the solar system, and so on. Another reason, another motivation for classifying on the basis of causal history has to do with explanation. And this pertains maybe more directly to the two of the examples that we just considered, the homologs in biology and the cognates in linguistics, where we classify things as homologous organs or homologous phenotypic features, or as cognates in linguistics, in order to understand the process of natural selection better, to understand certain kinds of selection pressures, to understand the evolution of languages, and so on. So it helps us, I think, explain certain features of how we got to where we are based on understanding the past history of these phenomena. In both cases, I would say, now, of course, retrodiction and explanation are often identified, retrodiction or prediction, I should say, or explanation are often identified as two central aims of science. And I think in both cases, what these classifications enable us to do is to serve the underlying goal of retracing and understanding the causal structure of the world. And I think in all these cases, what we're mainly interested in is causal origin or causal history and causal trajectories. And so I think that provides a great deal of the impetus for identifying categories on the basis of their history or origin. So it seems to me that etiological categories are the explananda in historical explanations. So let me try and expand on that a little bit and draw this connection a bit more explicitly between etiological classification and historical explanation. So here's an example of historical explanation. So just going back to the case of the homologous phenotypic features that I mentioned, here's a case where we have these three phenotypic features, which at first sight look quite different in three different mammals. So we have the foreleg of a feline, say a tiger or a cat of some kind, and a fin of a dolphin from a particular organism drawn from a particular species of dolphin, and a bat's wing. Now, functionally, causally, in many ways, they seem to be radically different. On closer inspection, of course, biologists notice that there are these uncanny similarities between, in the structures, in the way that the bones are related to each other in their configurations. And upon closer analysis, they realize that these similarities are not coincidental. They all derive from a common ancestor. So they posit some ancestral mammalian forelimb, which they all descend from. And this explains this uncanny correlation or resemblance between these three phenotypic features. And this kind of historical explanation has been discussed quite widely in the literature and philosophy of science, at least since Reichenbach in the mid-50s. But I think Carol Cleland, in a more recent paper, outlines the principle that lies behind these kinds of historical explanations. And she formulates the common cause principle, which was first formulated by Reichenbach as follows. She says, seemingly improbable coincidences, correlations, or similarities among events or states are best explained by reference to a shared common cause. So there's an interesting debate in the literature, which I won't have time to go into, about the status of this common cause principle and what it derives from. Why are we warranted to trace seemingly improbable coincidences to a common cause? When is that a legitimate form of explanation, and when isn't it? And what is it grounded in ultimately? Some people think of it as grounded in some basic metaphysical feature of the world. Other people think it relates to the second law of thermodynamics. And there's also an interesting debate about when we're warranted to use it. Should it be our default whenever we see improbable coincidences, or should we resort to it only under certain circumstances? Now, I won't go into that here, but suffice it to say that in many circumstances, when we see these kinds of improbable coincidences, we are warranted to trace them back to some common cause. And it seems to me that explanandum here is unified by being put into this etiological category. So once we identify this homologous phenotypic feature, that's when we can frame the explanation as to the common cause that enables us to explain this apparently puzzling coincidence. Here's another case from the ones that I mentioned a little while ago. When we look at cognate linguistic morphemes, so we look at some language like Sanskrit, and we notice that there is a word that has a certain phonological properties, and it also has certain semantic properties. And then we notice a very closely related word in another language, Persian, and similarly for ancient Greek, for Latin, and then for English. And then we realize that this is not just a coincidence. There's a reason that these languages all contain words that are phonologically very similar, and also semantically more or less the same, more or less identical. And so we trace them back, or linguists trace them back to some hypothesized language in the past, which they call Proto-Indo-European. Now, Proto-Indo-European is a language that we have no trace of directly. We don't have any, this is before, this is prehistory, this is before recorded texts. But on the basis of these kinds of uncanny similarities, linguists have posited the existence of a language which gave rise to these different languages. And I should mention in this case, in many cases, English borrows directly from Latin or Greek, but as I understand the etymology in this case, this is a case where English got it from previous Germanic languages, so it came separately to Greek and Latin. It didn't come to English from Greek and Latin. But in either case, what we've done here is also posited a common cause once we've seen these uncanny coincidences among these different words. And the common cause explanation enables us to explain these phonological, semantic, and other similarities among words in different natural languages. And it does so by positing a common origin. And again, the explanandum in this case is unified by being put in a single taxonomic category, whereby we think of this as, or these as cognate linguistic morphemes. So I've tried to show how etiological classification is typically underwritten by common cause explanation, and that's what motivates or justifies it in scientific inquiry. So homologs in evolutionary biology are classified according to their origin in ancestral features. Cognates in linguistics are classified according to their origin in proto-languages, such as Proto-Indo-European in this case. But you might raise the objection that, or at least raise a question, as to whether these explanations always group effects of a common cause in a single taxonomic category, or whether we're always required in order to frame these common cause explanations to identify a taxonomic category that groups them together. In other words, do all instances of the explanandum always belong to the same, to the same etiological category? Well, here would seem to be an exception. So to sort of drive this point home, consider the common cause explanation. This is a famous case, of course, for correlations among various phenomena at the Cretaceous tertiary boundary. So the boundary between these two geological time periods, the Cretaceous and the Tertiary, or I think now it's usually called the Paleogene, the KT boundary as it's often known, we find that there is this very intriguing crater in Mexico that we date back to around this time period. We also realized that the dinosaurs became extinct around this same time period, which is around 66 million years ago. And we also find in the geological record a layer of sediment or ash that seems to date to around the same period. And because of this kind of surprising coincidence, scientists framed the explanation that there was an asteroid impact around this time, which could explain these seemingly improbable coincidences in the geological record and in the paleontological record. But now you might say, look, the effects of this common cause are not grouped together in a single taxonomic category. We don't count the crater, the extinction, and the layer of sediment as somehow comprising a single taxonomic category or an etiological kind. So how come in this case we don't, this common cause explanation does not presuppose an etiological category or etiological classification scheme? Now, I don't know if I have a full answer to this puzzle or this question, but I guess in this case, it seems to me there are two things that maybe are obstacles that would prevent us from framing a single taxonomic category. One is that in this case, the effects of the common cause cut across broader ontological categories and scientific domains. So the asteroid impact at the KT boundary caused both a biological event, extinction, and a geological feature. Now, an event and a feature of the landscape are ontologically sort of belong to different categories, and they also belong to different scientific domains. One pertains primarily to biology and the other to geology, and that would seem to make it hard to group them together into a single taxonomic category. The other reason is, if we go back to Cleland's formulation of the common cause principle, she talks about correlations or similarities. So she talks about improbable coincidences, and she spells that out by talking about correlations or similarities. So maybe when we have mere correlations, there are fewer grounds to classify the effects within the same category, within the same taxonomic category. When there are more robust similarities, that's perhaps when we can frame a single category and classify them together in the same taxonomic category. But as I said, I don't have a full answer to that question. And if any of you are, have any thoughts on that, I'd be very interested, because I'm still trying to think through some of these questions. So to conclude, to wrap up, some philosophers claim that science should only be concerned with synchronic causal powers, that our inquiries should always be framed in terms of synchronic properties, not diachronic properties. But I think it's quite clear that classification according to causal history or causal origin, or as I'm saying, etiology is widespread in science. Etiological classification, as I said, can be pure or hybrid. It can be token or type, and I think there are instructive differences between these different kinds of etiological classifications. I've also mentioned that etiological and non-etiological, or diachronic and synchronic categories, can coexist in cross-cutting taxonomic systems within the same science, often, like homologies and analogies in biology. And I've also tried to say that etiological classification is justified both by prediction or retrodiction, to be more specific, and also explanation. And in particular, in both cases, I think the goal is to discern the causal structure of the world. And in particular, when it comes to explanation, it's motivated by framing these common cause explanations, although I've also conceded that some common cause explanations don't require us to come up with etiological categories. So I don't think it's obligatory to frame these explanations always in terms of etiological classification schemes. And I've indicated some reasons why I think in some cases that might be more feasible and a more natural thing to do than in others. But I'd also welcome any thoughts that people have about that issue. So I'm going to leave it there. I hope I didn't take up too much time, and there's some time for some discussion. Thank you.